This ordinary-looking Missouri road cut records a story that can fill geologists with a deep sense of awe and curiosity. The rocks here share this story with exposures found near the bottom of the Grand Canyon. This roadside site might not be as peaceful, but it's right here in the Ozarks and anyone can visit it. The story here is what geologists call the Great Unconformity, a massive gap in the geologic record that produces an intense desire to put a hand on either side and physically embrace an almost unfathomable span of time that's missing from the geologic record. If you've ever gone out to stargaze and felt a deep sense of awe at the vastness of space, well, that's how geologists feel about the depth of geologic time, especially when some goes missing. So today on Ozark Outsider, our goal is to help you experience this deep sense of wonder and curiosity as we explore the geologic story of the Great Unconformity in the Missouri Ozarks. Let's begin by taking a closer look at this specific exposure on Highway 72 west of Fredericktown. You know this site is special when even Google Maps marks it as the Missouri Great Unconformity Road Cut, a 5-star tourist attraction. We want to walk you through this outcrop story as if you were on site with us during a field trip to help you really understand what it's telling us. The rock at the base of this outcrop is a volcanic deposit related to a massive caldera eruption. See our previous video on the igneous history of the St. Francis Mountain region for the full backstory. At the top of the sequence here, there are clearly layered sedimentary rocks. Fossils aren't obvious at this location, but similar rocks in the area do preserve traces of marine life, indicating a shallow marine setting at the time that these rocks were deposited. In between the volcanic and marine sedimentary rocks, there's a conglomerate zone featuring generally rounded clasts of various sizes that appear to be derived from the volcanic rock below, but are bound together by finer-grained sediments. This tells us that the top of the older volcanic rock is an old erosional surface, covered first by the cobble deposit and subsequently by the younger layered sedimentary rocks. You can clearly see how the fine-grained sediments overlap the rugged surface of the conglomerate layer below. But this doesn't tell us how much time elapsed between the volcanic activity, the subsequent erosion, the formation of the conglomerate layer, and the final deposition of marine sediments. Was it quite rapid, geologically speaking, or was there a larger time gap? Two other clues from this outcrop provide more context. First, the exact boundary between the volcanic rock and the conglomerate is surprisingly difficult to define up close, in part because there's a zone of uppermost volcanic rock that appears worn and weathered. Based on analogy to modern conditions, this implies a fairly long period of exposure to the elements. But even more telling is this vertical feature cutting across the volcanic rock. It's visible across the road, too. In 3 dimensions, it's actually a roughly planar feature extended across the road cut. Countless eager geology students have investigated this exposure, resulting in its surface retreating deeply into the surrounding rock face. So if you visit this outcrop, just please be aware that unnatural overhangs like this can be especially unstable and dangerous. Basic geological reasoning tells us that this feature is younger than the volcanic rock because of the cross-cutting relationship. It is, in fact, a different igneous rock that intruded the volcanic rock as a dike. But both igneous rocks were cut off from the surface separating them from the sedimentary rocks above, which therefore must be younger still. Could this surface have been the top of the volcanic rock when the dike was emplaced? If so, you'd expect the dike's molten material to have spilled out onto that surface to some unknown depth, and there's no sign of that. Instead, the volcanic rock must have extended well above this location when the dike first intruded, but that overlying material is now missing, eroded away before subsequent deposition of the sediments we see today. A final piece of evidence is that the contact between the volcanic rocks and the overlying sediments is clearly sloped in this outcrop, but the overlying bedding is near horizontal and truncates against the older rock. This tells us that the earlier surface onto which the sediments were deposited was not flat, but had pre-existing topography, what geologists call paleotopography. Regional evidence clearly shows that this ancient land surface had at least 700 feet of vertical relief, something we explored in far more detail in a previous video. So let's summarize the story preserved in this outcrop. An eruption from a regional caldera complex produced thick volcanic deposits, later intruded by this dike, and others like it in the region. A subsequent period of erosion removed enough material to reshape the regional landscape. At some later point, sediments were deposited over this surface. First, a conglomerate layer partly derived from the underlying volcanic rock, then overlying layers of nearly horizontal marine sedimentary rock. The key point here is that significant time must have passed between the formation of the volcanic rocks and the subsequent deposition of sedimentary layers, but the evidence of just what happened during that time isn't preserved. A geologic feature like this, that documents a gap in time, is known as an unconformity. But so far we've only talked about relative age, and perhaps you're not sufficiently impressed yet. So let's add in some actual ages for context. As a quick reminder, Earth's geologic history is divided into 4 major parts, though of different lengths. For a brief summary of how the Ozarks fit into this timeline, check out our previous video, Ozarks by Era. The layered sediments at the Great Unconformity road cut date back to the Middle Cambrian, the earliest period of the Paleozoic era. These rocks are probably from the lowest part of what's called the Bonne Terre Formation. Let's take a moment to consider what's happened in all the time since those sediments were deposited. All of the overlying sedimentary rocks in the Ozarks were deposited. A continental collision that formed the distinctive folded bedrock of the Ouachita Mountains in central Arkansas influenced the Ozarks as well. Dinosaurs evolved and went extinct. Well, mostly extinct. Erosion has been shaping the landscape in an ongoing process. Glaciers nudged up against the very northern Ozark fringe, and mastodons, sloths, and giant beavers roamed the landscape. All that stuff and more happened in only about 500 million years. So how old is the underlying rock? Radiometric dates for the volcanic rock exposed here place its eruption at about 1.46 billion years ago. So the amount of missing time between the volcanic and sedimentary rocks is almost double the time period we just described. Just stop and think about that for a moment. That's a lot of time. From roughly 1.46 billion to roughly 500 million. Should we just call it a billion? Maybe, but keep in mind that involves rounding up by 40 million years, and that's kind of a lot, even for geologists. Precambrian igneous rocks like the volcanic deposits here represent the oldest rocks exposed in the Ozarks, so from here on we're going to shorten our timescale to match. One question we haven't quite addressed is where that intervening conglomerate layer fits into the timeline. The short answer is that it's not as well constrained, but it's much closer in age to the other sediments than to the volcanics. So while it nudges the end of the unconformity a little further back in time, it doesn't really change the scale of the near billion-year gap that we're focused on here. Just what happened during that ginormous gap in time? This could be considered one of the greatest mysteries of Ozark geology, based on the sheer scale of the missing record that defines the Great Unconformity. A lack of information is often the greatest way to pique the curiosity, so hopefully you want to know more because we're going to delve deeper. So far, we've focused on the Great Unconformity in this one location, but it extends way beyond that. The sedimentary rocks that dominate the modern Ozark landscape have to rest on something, and that something is the far older Precambrian rock that lies everywhere below, as we modeled in yet another previous video focusing on Missouri. In other words, the erosional surface separating the Precambrian basement rock from the overlying Paleozoic sedimentary rock, indicated here by the thick dashed line, is the Great Unconformity, everywhere beneath the Ozarks. Faulting and warping have added to the complexity of that surface, but we're not going to address that today. And this isn't just an Ozark feature. Precambrian rocks underlie much of North America, appearing at the surface in certain regions. Wherever old basement rocks are overlain by Paleozoic sedimentary rocks, you find the Great Unconformity, though details may vary from place to place. But most of the time, the exact contact is obscured. For example, here at Silver Mines Recreation Area in southeast Missouri, we could stand on Paleozoic and Precambrian rocks a few tens of yards apart, gazing at each other fondly across the Unconformity. But the actual contact was hidden beneath the soil and vegetation. Here at Tomsock State Park, we could find conglomerate beds suggesting that the underlying Precambrian rock was just beneath our feet, but again, it wasn't exposed. And here at Hahn State Park, Precambrian igneous rock is exposed along the Pickle Creek Valley, with Cambrian sandstone on the ridge above. The contact between these two represents the Great Unconformity, but we haven't found it clearly exposed here. There are certainly places across the country where the Unconformity is nicely exposed, and this map shows a selection of locations where it's pretty easy to get to. The most famous outcrop is in the Grand Canyon, where 1.2 billion years are missing from the geologic record. But the southeast Missouri Ozarks are an especially interesting exposure of this continental scale phenomenon, in part due to the rugged paleotopography on the Precambrian surface here, which we covered in more detail in yet another previous video. And we do have two very nice publicly accessible exposures. One on the Highway 72 road cut, with its wide shoulder for parking, and another in the Scour Valley at Johnson Shut-in State Park, where you really can see the exact point of contact between Paleozoic and Precambrian rocks. But the time gap this contact represents isn't the same everywhere. The stratigraphic column for Missouri contains a whole sequence of Cambrian-aged rock formations, all of which are exposed in contact with the underlying Precambrian rocks in different parts of the region. Collectively, these span tens of millions of years, so locally there's a lot of variability in the exact age of the upper boundary of the Great Unconformity. And down below, the Grassy Mountain ignimbrite is just one more part of a much more complex suite of volcanic and intrusive rocks that collectively date within a span of about 30 million years, once again introducing a lot of variability in the lower boundary of the Great Unconformity. And there's yet one more wrinkle. Around 1.3 billion years ago, another set of igneous rocks intruded into the older material. Where these relatively younger igneous rocks are exposed by later erosion and overlain by Cambrian sedimentary rocks, the time gap of the Great Unconformity is notably shorter, but still awe-inspiringly vast. So what happened during all that missing time, however long it lasted? One clear answer is erosion, but one clear question is how much. Let's visit one of Missouri's most popular geologic sites for some very interesting insights. One example of these younger 1.3 billion year old rocks, known as the Graniteville Granite, is on display at Elephant Rock State Park. A short walk into the surrounding woods reveals evidence of sedimentary rocks nearly level with the igneous bedrock, telling us that the Unconformity is close by and probably extended just above the rocks exposed here. Unlike the Highway 72 road cut, where the rocks below the Unconformity came from a large caldera eruption, the rock here at Elephant Rocks is granite, an igneous rock that cooled underground. And this granite has beautiful coarse crystals, implying that the magma cooled quite slowly, well below the surface. So, how does rock that formed deep underground end up having marine sediments deposited directly on top of it? Let's think about a generic granite pluton. The granite intrudes into pre-existing bedrock at some depth, where it cools slowly, forming those beautiful big crystals. But to expose this rock at the surface, there has to have been a substantial amount of erosion, perhaps combined with extensional faulting. So what was the emplacement depth of the Graniteville Granite? Surprisingly, we have not found a number in the geologic literature. So we'll use 3 lines of evidence to come up with an estimate. First, a new paper from Yellowstone shows the depths of modern magma chambers with varying compositions. The 2 red chambers, marked C6 and C7, are compositionally similar to granite, though they aren't yet granite because they're still partially molten. C6 spans a depth of 4 to 13 kilometers, and C7 extends from 6 to 12 kilometers. So even the shallowest parts of these magma chambers are still 4 to 6 kilometers down. Second, the Graniteville Granite at Elephant Rocks was intruded into volcanic rocks formed during the earlier regional phase of igneous activity. How thick was this sequence? The Grassy Mountain ignimbrite alone, which we saw along Highway 72, is reported to be at least a kilometer thick in places over an area of 50-some square kilometers. The calderas were capable of erupting a lot of material. This report mapped the distribution and thickness of many different volcanic units. If you add up all the individual units, you get a rough total thickness of around 4 kilometers. In reality, these weren't a simple vertical stack, but the total volume and depth of volcanic rock associated with regional caldera eruptions and intrusions was considerable. And this lets us assume that this granite, which we know intruded into the volcanic rocks, still had multiple kilometers of rock overhead when it cooled. Finally, a thermochronometry dataset, linked below, which offers insight into the thermal histories of rocks, seems to be compatible with the idea that the Precambrian igneous rocks, now at the surface regionally, were once at a depth of 4 to 6 kilometers. So, from the time that the Graniteville granite first cooled underground at around 1.3 billion years ago, to the time when this part of it was exposed at the surface by erosion no later than around 500 million years ago, a thick sequence of hard, overlying igneous rock had to be removed by erosion just to get to the point where early Cambrian seas could be lapping at the exposed granite. And even if the Graniteville granite was shallower than we're suggesting here, don't forget that kilometers-thick sequence of volcanic rocks laid down in the earlier pulse of igneous activity, much of which also must have been eroded away to leave behind the regional exposures we see today. This raises all sorts of fascinating questions. What did the landscape look like 1.3 billion years ago when the Graniteville granite was first emplaced kilometers beneath it? How did the topographic relief evolve in the 800 or so million years that followed? Were there episodes of deposition that left no modern trace? What role did faulting or other structural deformation play? How rugged was the paleotopography of the early Cambrian when this granite was finally exposed after kilometers of rock had been removed? And how did it change further as Paleozoic seas inundated the landscape? These are all questions whose answers are obscured by the missing time represented by the Great Unconformity. And what was it even like for a landscape to erode back then? After all, many of the factors that contribute to modern landscape erosion were really different back in the Precambrian. No vegetation to protect the surface from the elements, but also no vegetation or lichens to help break up rock. No worms to turn soil. What is landscape erosion like when complex life has yet to evolve? Let's take a look at life in the Cambrian and before. The Cambrian period has long been known for a pulse of diversification in complex life, with various taxonomic groups appearing for the first time in what is commonly known as the Cambrian explosion. This includes everyone's Paleozoic favorite, the trilobite. The fossil evidence for this rapid diversification is recorded in a near simultaneous appearance of major sedimentary rocks in the geologic record. This leads to one of the various geologic mysteries entangled with the Great Unconformity. Did rising seas inundating a big continental platform pave the way for diversification? Or was life diversifying earlier than previously thought, but missing parts of the geologic record conceal this development? Questions like these have been pondered by countless geologists for well over a century. So here's the timeline we've established so far for the Great Unconformity in the Ozarks. Though this feature extends well beyond the Ozarks, it's not geographically universal, and outcrops from various parts of the world have given geologists insight into the big picture of what happened during this time from a global perspective. The first geologist to recognize the Great Unconformity did so before the development of the plate tectonic paradigm. But we now benefit from understanding that tectonic plates have been rearranging themselves on Earth for well over 2 billion years. Periodically, supercontinents form. You've probably heard of Pangaea, which formed and then broke up into today's modern continents. But an earlier supercontinent, Rodinia, assembled and then broke up in the time frame relevant to the Great Unconformity gap, though the details of continental configurations are still debated. Could a global-scale process like plate tectonics directly lead to a feature as geographically widespread as the Great Unconformity? Did continental collisions and subsequent rifting drive patterns of global mountain building, subsidence, and sea level change that relate to the formation of the widespread Great Unconformity? Another major event within the time gap is known as Snowball Earth, a period for which there's evidence of major glacial events that probably extended their reach even to equatorial regions. glaciers are particularly effective at eroding landscapes. More specifically, did snowball Earth contribute to the extensive erosion we've been discussing? Conceptually, this seems plausible, but is there any direct evidence of Precambrian glaciers in the Ozarks? Some of you might be thinking, oh, hey, the elephant rocks look like giant glacial boulders. Sorry, but we can state unequivocally that the elephant rocks are not glacial boulders, though that's a topic for another day. But if you want to be pedantic when someone tells you there were never glaciers in the Ozarks, you can point out that maybe there were during a long ago Snowball Earth episode. Just please don't confuse a possible glaciation 700 some million years ago with the Pleistocene glaciers of the last 2.5 million years that affected North Missouri but did not reach meaningfully into the Ozarks. To our knowledge, no one has gone as far as interpreting features of the unconformity or paleotopography in the Ozarks in a glacial context. It's also worth noting that something like 100 million years elapsed between the last of the generally accepted snowball Earth glaciations and the onset of inundation by Cambrian seas. That's a pretty long time. Would it be enough to obscure traces left by snowball Earth glaciations? So we want to revisit the question of erosion one more time. Geologists can look at many present-day physical processes and assume that things behaved similarly in the past. For example, ripples forming in sand are subject to essentially the same physical processes now as they were in the deep past. But the erosional history of the time period spanned by the Great Unconformity remains shrouded in mystery. Can we assume that our understanding of erosional processes in the last few million years of geologic history would apply to a time period 1 billion years ago? In the Precambrian, did rocks erode more stubbornly or less stubbornly than today? Are we even sure that the entire period was one long period of erosion, as opposed to some now obscured periods of deposition? Based on the framework we've presented so far, let's say we have 4 to 6 kilometers of rock to erode regionally, and 800 million years since the emplacement of the Graniteville granite in which to do it. Erosion would need to remove, on average, 5 to 8 meters of rock per million years during this time frame. That average is pretty comparable to more recent rates relevant to the Ozarks, where 2 regional studies found basin averaged rates in the range of 4 to 15 meters per million years. And modern erosion rates estimated for more tectonically active and topographically rugged landscapes can be far higher, again suggesting that the long-term amount of Precambrian erosion we're discussing here is entirely feasible. Our geological intuition says that the St. Francis Mountains once stood much taller than they do today, or did at the start of the Cambrian. It's likely that kilometers of rock eroded away over the course of 800 or more million years. The ancestral St. Francis Mountains became the St. Francis Nubbins, as erosion, in combination with faulting, exposed the innards of former calderas, from volcanic deposits erupted onto the surface, to intrusive rocks that cooled underground from related magma, to younger intrusions like the Graniteville granite. All of this was exposed at or near the surface by around 500 million years ago, when the remnant nubbins, literally reduced to sea level but still with enough topographic dignity to temporarily form islands, were drowned by Paleozoic seas and buried in sediment derived locally and from afar. Of course, today's St. Francis Mountains are back up above sea level again, having been re-exposed by another round of uplift and erosion that mostly removed the younger overlying sediments. But that's a story for another day. The remaining geologic record tells us that these things must have happened, but so many questions and uncertainties surround the Great Unconformity, in Missouri and elsewhere. It's like being given a great mystery novel, with the first and final chapters intact, but a large chunk of the central narrative has been torn out. You know how the story starts and how it ends, and can extrapolate a certain amount of the plot, but you don't know just how it all unfolded. Even a trained geologist's mind struggles to comprehend the timescales and implications of this. And yet, we can reach out and touch either side of that gap in time, embracing nearly 1 billion years in a human arm span. It's simply awe-inspiring. It's fitting that a video about a long time gap took us over a year to finish. This has been a challenging subject to interpret both accessibly and accurately. Let us know how we did in the comments. And if you're in a position to offer financial support for the work it takes to produce these videos, Feel free to hit the thanks button below or leave us a tip via our Ko-fi page, where a higher percentage of your support goes to us. We're so thankful to all the viewers who have helped our channel continue to grow.